Anything before 62. Maybe I should say that. Anything before 62. Okay. All right. Now 62 and f of g. Now, more than likely, you get this first one. Okay. And that's the only reason I think is in my book they give me this answer. If you factor out a negative, a lot of times they like to write things with positives if they can. You can factor out a negative and then just kind of put it out in front of the whole thing. Do you have to? Absolutely not. But that's just kind of where that comes from. We got to make sure we understand the domain, and then we also need to be able to get ADA as well. All right, 62. Anthony, since we were just doing that, what's the two cases there? F of x is what?
1 over x minus 1.
And what's g of x?
2 over x plus 3.
And then we are asked to find f of g of x, right?
Yeah.
Okay, so f of g of x. Aiden, do you know how to even just set it up to begin with? Just that question. Do you know what this means here? How I would evaluate that?
I think so. You like put g of x somewhere?
Somewhere. That's a good way to word it.
I'm not sure.
It goes in for the end of the function wherever the x is. Okay, wherever the x is. So now this 1 will stay, this minus 1 will stay, this x now it gets replaced by that. So it becomes 1 over 2 over x plus 3 minus 1. Agree? Oh, thank you, Dakota. Thank you. Yes, one head nod. All right, so we agree. Dakota agrees, not we. I'm sorry. Dakota agrees. So you got this part here. Now that's the easy part. You've done the composition. You just now need to do the algebra, which is the hard part. Is just simplify everything. Well, I'm going to get a common denominator on this one, and on the other one I'll multiply to get rid of everything. Here, this is 1. This is 2 over x plus 3 minus 1. You can think of that as 1 over 1. But you got to multiply both the top and bottom of this by x plus 3. And so I still get 1. I get 2 over x. Let's see here. Let me just make this whole thing over x plus 3. Think of this as 2 minus 1 times x plus 3. You got to distribute that negative or distribute that negative 1. So a lot of times people just forget to do it to the 3 as well. So now I got 1 over, that's 2 minus x minus 3 over x plus 3, which is negative x minus 1 over x plus 3. So we're close. We just got to do the last step. Keep, change, flip. Keep the top exactly how it is, which is just a 1. Change it to multiplication. Flip. And so this is where I get x plus 3 over negative x minus 1. Domain for f of g of x. We are plugging, so if you were asked to find, I'm just throwing this out there, f of g of 5. Matthew, you weren't here yesterday, right?
Correct.
Correct. All right, how do you do f of g of 5?
You do g of 5, and then you get that, and then you put that into f.
What's g of 5? Just look up here.
G of 5 is 2 over 8.
Which is 1/4?
Which is 1/4.
1/4. So I plug in 1/4. So g of 5 is 1/4. And so I take that and I plug it into f. What's f of 1/4? So 1/4 minus 1 is negative 3/4. 1 divided by negative 3/4. Matthew is obviously what? Correct.
Yeah.
Negative 4/3. Does it have an answer?
Mm-hmm.
So that means that 5 is in the domain. 5 is in the domain. So we don't want to go through all the answers, right? What won't work when I plug it into g of x?
Negative 3.
Negative 3's got to be out. We toss negative 3 out. So x cannot equal negative 3 because of the g of x. Then you have to take a look at your final answer, which was f of g of x. is x plus 3 over negative x minus 1. What won't work there? Is it negative 1? Yep, negative 1. So I got to throw that out. So that leaves me negative infinity to negative 3, union negative 3 to negative 1, union negative 1 to infinity. Okay? Now, a lot of times it comes into the case, well, why don't I have to throw out 1? Okay, 1 will work. If I plug in 1, take a look what happens. What's g of 1? 1 plus 3 is 4. 2 forces 1/2. Now I plug 1/2 in. I get 1/2 minus 1, which is negative 1/2. So I end up with negative 2. It gives me an answer. What doesn't give you an answer is, ouch, oh my goodness, my knee just about went out. I'm okay. Dakota might be the only one that cares. Thanks for worrying about it. But when you plug in negative 1, what happens? Negative 1 plus 3 is 2. 2 divided by 2 is 1. And then when you plug that in, that's where it gets undefined. So you got to throw those 2 out. So that should be our domain. All right, 82. Original ones. Matthew, you got the original ones handy?
I do. No, I don't. Never mind.
Anything?
Wait, no, I don't.
Oh, who's got them? Just anyway. All right, Brooke.
X plus 2 over x minus 3,
Okay.
and then x plus 1 over x minus 1.
All right, can somebody confirm?
Yeah.
All right, good. All right, so at least want to make sure we got those right. All right, is it f of g of x we're looking for? Or g of f of x? Do you not have it written on your paper? Why would you not do that? Why do you people not do those little things? It is infuriating. F of g of x. Well, I'm going with that. Unless somebody tells me otherwise. Okay? All right, so that looks like you take g, plug it in for both those x's. So x plus 1 over x minus 1 plus 2 over x plus 1 times x minus 1 minus 3. All right, now I said we can do this. This is the other way to do it. You can multiply by the same thing to get rid of fractions, which would be x minus 1 times x minus 1. This, quite honestly, is quicker, but doesn't mean it's easier because I just see more mistakes this way. Just letting you know that. But when I do this, it cancels here. So you're left with x plus 1. And then you do have to multiply plus 2 times x minus 1. Cancels here. And so you're left with x plus 1 minus 3 times x minus 1. So I don't have any fractions. 2x plus x is 3x. Negative 2 plus 1 is minus 1. Negative 3x plus x is minus 2x. Positive 3 plus 1 is plus 4. So you get there quicker if you don't make a mistake. All right, what can't x equal? What are we plugging into first? We're plugging into g of x first, right, Brandon?
Right.
What can I plug into g of x?
1.
1. So x cannot equal 1. What can x equal here? 2, right? That's where we get our domain. Negative infinity, 2, 1. No, yes. Union 1 to 2. Union 2 to infinity. All right, we agree with all that? Is that what I had here? Or go. Yes, so that's what we had there. Okay. Takes a couple times to do it. Okay, sometimes it takes more than one time to go back through it. All right, to make it sink in. All right, we are going to section 2.9. Okay, on those guided notes. This is the last section of the chapter. Okay, last section of the chapter. We're still good. Test Monday. It'll be the multiple choice part, and it'll probably be about a little more than half the period. Give you time. And then the second part is Tuesday. Okay, so we can fit it all in. All right, define an inverse function. Find the inverse function. All this good stuff. Inverse function, does that mean anything to Brandon at this point?
No.
No, nothing. Okay. All right, well, let's see if at the end of the period you still say the same thing. Hopefully I'll do something. All right, fill in this chart. This is not a hard chart. Obviously, you're dealing with two easy functions, but make sure you look. They're not the same x values. Okay, just fill them in if you haven't already done so. You can graph them if you want, but I'm actually not going to spend much time on the graph. Got it? All right, Andrew, what do we got here?
I got 0, 1, 2, 3, 4.
And then for the second one?
-2, -1, 0, 1, 2.
Okay, so make sure you pay attention. It's not -2 to 2 in that second one. All right. F of x and g of x are inverses. Okay, I'm telling you that now. Since g of x undoes what f of x did. Now, let me explain what that means. Okay? That's probably like you're going like, what? All right. For this point here, -2 went to 0. G of x, when I plug in 0, what do I get back? -2. -1 goes to 1, 1 goes to -1. 0 goes to 2, 2 goes to 0. So I want you to think about this. What is f of g of 5? Okay, let's take a look at that. I didn't really write that down right. Hold on. Okay, what's g of 5? 5 minus 2 is what? 3. What's f of 3? 5. Okay, f of g of 5 equals what? 5. What's f of g of -7? -7 minus 2. -9. -9 plus 2. -7. What's going to happen each time? You're going to end up with what you started with, right? So if I do, now it doesn't matter, I can go the other order. G of f of 10. F of 10 is 12. G of 12 is 10. So it doesn't matter what I start with, I'm going to end with the same number. Does that make sense? This means they're inverses. That's how this works. Okay, so I take one number, I plug it into that function, I take that answer, plug it into the other function, it takes me right back where we were. Okay, it takes me right back where we were. Okay, let's add something here to the word function. A function is called a one-to-one. One-to-one function. If each y value in its range corresponds to only one x value in its domain. Now you don't have these pictures on your graphs, just pay attention. First of all, is it a function? Is this one a function? For a function, each x goes to one y. We have an x that goes to two y's. Not a function. It can't be one-to-one. It's not even a function. Is this a function? Does each x go to one y? Yes. But is each y paired with only one x? No. So this is not one-to-one. But it is a function. Okay, it's not one-to-one. So to be one-to-one is exactly like it sounds. Each x goes to one y. You can't be paired to more than one y. How does that look like on a graph? Okay, don't draw this down. Don't draw this. A parabola. Is a parabola one-to-one? First of all, is it a function? Does it pass the vertical line test? Is it one-to-one? No, because here's why. Because there's a y value, specifically 4, where -2 goes to 4 if for x squared. 2 goes to 4. Can't have that. So for a function to be one-to-one, it must pass a horizontal line test. It means a horizontal line cannot hit it twice. Well, what would a graph look like that passes the vertical line test and horizontal line test? Something like that. Okay? You cannot have a change in direction, because once I have a change in direction, what happens once I go do this? Can that be 1-to-1? Nope. Fails the horizontal line test. Okay, so that is going to limit our options. That's okay though. All right, a little bit into some of the terminology here. If f is a 1-to-1 function, then the inverse of f is also a function. The inverse function is denoted with this symbol here. Now, it doesn't have the square around it. That's just, I don't know why that's there. And it is read the inverse of f, or f inverse. You don't say f to the -1 power, and it is not a power. It is just saying the inverse. It's talking about another function. Okay, so when you see that we're not doing a -1 power, it doesn't mean 1 over f. It's the inverse. Okay? So that is the case. Because one undoes the other. So this is, we're still on here. So if f of x equals y, this is where you got those little asterisks there. If f of x equals y, then f inverse of y equals x. Automatically. Okay. If f of 2 equals 8, then what can you tell me? F inverse of 8 equals 2. Okay, that's it. That's what it means with numbers. If xy is an ordered pair of f, then yx is an ordered pair of what? The inverse. The inverse. Okay. Now this leads to something with the composition of functions, which we did earlier. We did f of g of x, and we always got back x. So you see this inverse function property. Let f denote a 1-to-1 function. Then this is always going to be true. F of f inverse. This is the definition of it. It will always equal x. And then we always got the statement for every x in the domain of f inverse. And then f inverse of f of x is going to also equal x for every x in the domain of f. Okay. All right, once you get that down, flip it over. So just applying some quick principles here. If f of 2 equals -6, then I got a little bit different here. Same idea. What's f inverse of -6 equal? Dakota? 2. You with us? All right. So f inverse of -6 equals 2, what we talked about earlier. If f inverse of 8 equals 14, then what is true? 8, what's true?
Then 14 for f 14 equals 8.
F of 14 equals 8. Good. Always takes us back to where we started. It doesn't matter whether you start with the inverse or if you start with the function. If f of 8 equals y, then what must be true? Then f inverse of y equals 8. F of f inverse of 12 will equal, don't think too hard, 12. That equal 12. And then for that last one, if f inverse, it doesn't matter the order, f inverse of f of 7 is going to be 7. Okay, those are things we know they're inverses. Okay. All right, how do we graph these things? Here's there's your original function. How do I graph the inverse? That's all you got. How are we graphing the inverse? Good challenge for you, Matthew. Cosine.
You would flip x and y.
Exactly. Okay, we went back and we've said if for f of x, if there's a point on it, then the inverse must contain the flip of it. Okay, like that. So find some points. So right here, this is negative 6, 0. This is 0, 6. This point here is 6, 6. And then let's flip them. Do not negate them. Just flip them. So negative 6, 0 becomes 0, negative 6. 0, 6 becomes 6, 0. What about 6, 6? What does that become? 6, 6. It'll just stay the same. All right, and then connect. There's the inverse. Okay, there's the inverse. All right, now I think you have on your paper, you have some points, like whether you have dots there. Okay, for the next one. So let's, I think here, 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 and I don't know why I went to this one here. What is that? 1, 2, 3, 4, 5, 6. 6, 5, 0, 2, negative 4, 0, negative 8, negative 2. All right, so you got those points. The inverse, flip them. Okay, that's all you do. So where is the negative 8, negative 2 becomes negative 2, negative 8. 1, 2. All right, so watch that. Negative 4, 0. 0, negative 4. 0, 2. 2, 0. And then 6, 5 becomes 5, 6. Connect those. What did I do wrong? Oh, I didn't put the negative 4 in the right spot. 0, negative 4. That should be 1, 2, 3, 4. There we go. Now it matches up. Okay, so there's your inverse. All right, take a look at that third one. See if you can identify any key points. And obviously the more the better, but it just depends. Now there should be an arrow on this one going to the right. Okay, it starts at negative 4, 0. Okay, that is a definite stopping point or starting point, okay, for that. All right, now, negative 4, 0, that means I get 0, negative 4, which would be right here. I also have negative 3, 1, which should be 1, negative 3. I have 0, 2, which should be 2, 0. And it looks like 5, 3, which should be 3, 5. There's our graph. All right, there's some symmetry here. What are those two graphs symmetric about? Not the origin. Why not? Here's why not. The origin is if you have a point, like this point here, you got to go through the origin. It has to be matching on the other side. So that would have to be, so remember, if x, y is a point, negative x, negative y is a point. So it's not the origin. So actually, if you think about it, f of x and the inverse are reflections about the line y equal x. Okay, about that line. Now, what is that line? What does that line look like? So let me just draw that in. You probably can draw it in from what you got there. So if I go this dotted line, remember it has a slope of 1, goes through the origin. Okay, that's the line y equals x. Okay, you see the symmetry there? If I draw it up here for these two. Okay, and then here. Okay, there's your symmetry. So geometrically, you got a reflection on y equals x. Algebraically, you flip the x and y coordinates. Okay, for that. All right, how are the domain and range related? So think about this. This is really big for inverse functions. Here's what's happening. We're taking an x value. We're plugging it into the function. We get that y value. We plug that into the inverse. We get back the same x value. So the range of the function is this y value gets plugged into the other. That's going to be the domain of the inverse. Okay, they got to be the same. And we said we always get back what we started with, which means that the domain of the original function has to equal the range of the inverse. Right, so those got to be equivalent. All right, once you have that, I think we're done with the bottom there, right? Flip it over to the other side. All right, this is just a quick summary of everything we've gone over. A function must be 1-to-1 to have an inverse function. Now it can't, if it's not 1-to-1, it'll have an inverse, but it just won't be a function. It's a detail that is important, but it doesn't like restrict you from getting an inverse. You can still get an inverse, it's just not a function. All right, I know this isn't on your guided notes, but all that means is it's strictly increasing or strictly decreasing. That's the only way you can get, only these graphs have inverse functions. Cannot have a peak or a valley. All right, what's that second one? Ooh, this is a good one. We didn't go over this directly. We didn't go over that directly. So what do you think about this one? For a table of ordered pairs to have an inverse, no y value must appear twice. Good. Or more than once. Either way you want to word it. I think I got more than once, but no y value may appear. And if it does appear twice, that would take care of that. If PQ lies on the graph of f of x, then what's true? Matthew?
QP.
QP lies on the graph of the inverse of f inverse of x. The range of f of x is the domain of the inverse. And then the domain of the function is the range of the inverse. And then lastly, what does f inverse of f of x have to equal? X. They both equal x. Okay? They both equal x. So there you go. That's basically all the inverses here. Now we're going to do one problem here. One problem together. All right. Verify the following are inverses. So f of x equals 1/2 x plus 2, and g of x equals 2x minus 4. I am telling you they're inverses. You're verifying that. So just think, don't write this down yet. Don't write anything down. But according to that, if I do f of g of 8, what does that have to equal if they're inverses? Got to equal 8. Well, let's just kind of mentally check it. G of 8 is 16 minus 4, which is 12. A half of 12 is 6. 6 plus 2 is 8. But you can't test every problem. You can't test every number. So how do we do this for every case? So to do this, to cover all our bases, what we have to do is we have to show that f of g of x will always equal x. And I got to show that g of f of x will always equal x. So you just can't plug in individual numbers because there's an infinite number of numbers you technically would have to test. You might have an idea whether it's true, but this proves it true for everything. So we're going to show that this always works. Now you got to show both cases. And even though this one isn't difficult in terms of the algebra, you got to show me those steps. You just can't just jump to the end. So what does f of g of x look like? F of g of x is 1/2. The g of x of 2x minus 4 goes in for the x plus 2. Show me those steps. Distribute the 1/2. I get x minus 2 plus 2. And that gives me what? x. So there's 4. That's f of g of x. All right, you plug in g of f of x. Show the steps. And so g of f of x, that has to look like 2 times 1/2 x plus 2 minus 4. That gives you x plus 4 minus 4, which equals x. So I've showed they're both true. Now, honestly, I've never had come across a case where one of them equals x and the other one doesn't, but mathematically I need to show both. In the end here, therefore, these 3 dots, there's a math kind of no shorthand for the word therefore. Therefore, f of x and g of x are inverses. Inverses. Okay. So that's, if it asks you to verify, you do that. Okay, a couple things, a couple problems just to kind of get us started for tomorrow. We'll finish up section 2.9 tomorrow. Start with you. Okay. What is that?